13.8 billion years ago, something extraordinary happened. From a point smaller than anything the human mind can picture, the universe exploded into being. Space, time, matter, and energy, all at once, were born in a single, blinding instant we now call the Big Bang. Everything we see, everything we are, and everything we may ever know emerged from this one unimaginable event. But what if we dared to ask the forbidden question? Not how the universe began, but what came before. A question that seems to defy meaning itself, because before time, there was no before. The deeper we look into the origins of everything, the stranger the answers become. Our equations fall apart. Logic turns into paradox. And what we find waiting beyond the edge of time is not empty space, but a realm where even nothingness is unstable, where the very laws of reality unravel. This is where our journey begins, not in the comfortable glow of galaxies, but in the absolute mystery of what might lie behind existence itself. Prepare to let go of all assumptions, to explore the questions that stretch science to its limits and reason to its breaking point. Welcome to the edge of the knowable. Welcome to the impossible. What do you see when you imagine emptiness? A blank void, a silent nothing stretching forever. For centuries, philosophers and scientists thought of empty space as the ultimate absence, a stage on which the universe plays out its drama, but otherwise devoid of substance. But modern physics tells a very different story. In the quantum realm, even the most perfect vacuum is anything but empty. It is alive, buzzing, flickering, seething with invisible activity. What appears silent to our senses is, in truth, a cosmic storm hidden beneath the stillness. Quantum mechanics reveals that what we call nothing is actually filled with restless energy. This invisible sea is called the quantum vacuum, a foundation where particles are constantly born and destroyed in a frenzy of momentary existence. These ghost-like entities are called virtual particles. They appear in pairs, live for the briefest flashes of time, then annihilate each other and vanish. They do not leave behind debris or memory, yet their presence shapes the universe in ways we can measure. They are not science fiction. They are fundamental to how reality behaves. Try to remove all matter from a region of space. Suck out every molecule, atom, and particle. Cool it to the lowest possible temperature, approaching absolute zero, minus 460 degrees Fahrenheit. Still, the energy will not go away. Even then, space continues to vibrate with a subtle force. This irreducible energy is called zero-point energy, and it exists because of Heisenberg's uncertainty principle, a law of nature that forbids total stillness. The universe simply refuses to be perfectly quiet. Something always stirs, even in the absence of everything. Physicists have measured the effects of this invisible motion. In a famous experiment called the Casimir effect, two metal plates placed very close together in a vacuum feel a force pushing them toward each other, not because of gravity, not because of magnetism, but because the space between them allows fewer quantum fluctuations than the space outside. It is a tiny push, yet it proves the point. Empty space is not empty. It is a dynamic fabric laced with energy, vibrating with potential, constantly borrowing and returning energy in a balance so precise it slips past our everyday perception. These quantum fluctuations are not limited to tiny effects. They may be the origin of everything. Some theories propose that the entire universe, the stars, the galaxies, the laws of nature, emerged from a quantum fluctuation in this vacuum. A momentary hiccup of energy that, instead of vanishing, grew, expanded, and became reality as we know it. In this view, our cosmos began not from something, nor from nothing, but from a strange in-between, a quantum vacuum that was never truly void, but always full of unrealized possibilities. So when we speak of emptiness, we are speaking of illusion. When we peer into deep space and imagine darkness, we are looking at a medium rich with creation. The quantum vacuum is not a passive backdrop. It is the engine room of existence, and it forces us to rethink what it means to say that something exists. In this ocean of seeming stillness, the very seeds of universes are always bubbling just beneath the surface. One of those seeds became us. The rest, perhaps, are still waiting to be noticed. Imagine nothing, not empty space, not darkness, not silence, but the complete absence of space, of time, of being. A void so absolute that even the word void loses meaning. It seems like the final boundary, an eternal stillness where nothing ever was or could be. But quantum physics dares to suggest otherwise. It whispers that even this perfect emptiness is unstable, that in the absence of all things, something strange begins to stir. The laws of quantum mechanics do not allow perfect stillness. Even nothing, it seems, must do something. According to the uncertainty principle, energy and time are linked in a peculiar relationship. The less time something exists, the more energy it can momentarily borrow from nowhere. In this way, the vacuum, though empty, can flicker. Tiny fluctuations appear, borrowing energy, spawning pairs of virtual particles, and then vanishing. This is not metaphor, it is physics. It happens all around us, in every corner of space. So what if, once, one of those fluctuations was not so tiny? What if it did not vanish, but instead, inflated? This is where one of the most daring theories in cosmology begins. It proposes that our entire universe, everything we know and observe, began as one of these quantum fluctuations, a momentary spark of energy that, by random chance or by the nature of the vacuum itself, grew. Not slowly, not even at the speed of light, but faster. In a fraction of a second, this tiny bubble expanded, stretching space itself outward at inconceivable speed. This process is called cosmic inflation, and it may have created everything. To picture it, imagine a soap bubble forming on the surface of water. But in this case, there is no water, no surface, no air, no outside at all. The bubble creates the surface as it grows. The space inside the bubble becomes space itself. The size, the laws, the shape of the universe, all encoded in the way that bubble expanded. What was a microscopic fluctuation becomes galaxies, stars, planets, and people. Time begins to tick. Gravity awakens. The void becomes cosmos. This model answers some of the deepest puzzles in cosmology. Why is the universe so uniform in all directions? Why does it appear flat, not curved? Cosmic inflation, starting from a quantum fluctuation, explains these with elegant precision, but it also raises new and thrilling questions. If a fluctuation could give rise to our universe, what stopped it from giving rise to others? Perhaps it did not. Perhaps it never has. Perhaps bubbles like ours are forming all the time, in places we will never see. From the outside, if there even is an outside, we would be just a speck, a single expanding bubble in an infinite quantum ocean. Our origin would not be a unique event, but one ripple in a sea of eternal creation. This is the unsettling, beautiful suggestion of quantum cosmology, that something can emerge from nothing, not through magic, but through the very laws of physics, and that nothing, true nothing, might be the most fertile ground of all. For most of human history, the word universe meant everything. The totality of existence, the whole of space and time. One cosmos, born in fire, expanding through the void. But what if that idea is too small? What if our universe is not the only one, but just one bubble in a vast cosmic ocean? An island among countless others. Not only is this possible, it may be inevitable. The deeper we peer into the mathematics of quantum theory and cosmic inflation, the more the idea of a multiverse emerges, not as fantasy, but as consequence. It begins with inflation, the sudden, violent expansion that shaped our universe in its earliest moments. But inflation, once started, does not easily stop. Instead, it may continue forever, like a wildfire spreading across a field, leaving behind bubble universes wherever it cools. Our universe is just one such bubble. Others may be forming right now, far beyond the limits of our observation, each born from its own fluctuation, each expanding, evolving, and existing with its own laws, constants, and dimensions. The multiverse is not an option, it is the prediction. In this grand framework, every possibility that quantum physics allows becomes reality somewhere. There may be a universe where gravity is stronger and stars live for only minutes. Another where electrons are heavier and chemistry is impossible. Most of these worlds would be sterile, chaotic, incapable of life. But a few, just a few, might have the right conditions for structure, for stability, for thought. The reason we find ourselves in a universe tuned for life may not be because it was designed, but because in the multiverse, all universes exist, and only some allow beings like us to ask why. Picture the multiverse like a pot of boiling water. Each bubble that forms is a universe, expanding with its own internal reality, never touching the others. The boiling never stops. Universes form endlessly, separated by regions of still inflating space that grow faster than light itself. Even if you could travel at the speed of light forever, you would never reach another universe. The space between them grows faster than any journey can cross, yet the possibilities they contain are infinite. This vision reshapes our understanding of what is possible. Somewhere in the multiverse, there may be a version of you who made a different choice. A version where Earth formed closer to its star, or not at all. A version where the constants of physics allow time to run backward. A version where civilizations arose in the hearts of neutron stars. If it can happen, then somewhere it does happen. Not because imagination demands it, but because the equations allow it. And the multiverse cannot help but realize it all. Yet, with this grand idea comes a deep philosophical shift. The multiverse suggests that we are not central, not unique, not even necessary. We are not the product of a perfect plan, but of cosmic statistics. In an infinite collection of realities, it is not surprising that one would look like ours. What is surprising is that we have the awareness to wonder about it, to look up and ask, "Is this all there is?" And to hear the universe quietly whisper back, "No, one universe is not enough." At the deepest levels of reality, beneath atoms, beneath quarks, beneath even the smallest particles known to physics, lies something stranger, something more fundamental. According to string theory, the smallest units of nature are not points, but tiny vibrating loops of energy. These strings are unimaginably small, far beyond the reach of any microscope. But their vibrations form the particles that build our universe. Like the strings of a cosmic instrument, each unique vibration gives rise to a different fundamental particle. Electrons, photons, quarks, all simply different notes in the same eternal symphony. String theory does not stop with these vibrations. It requires more than the 3 dimensions of space we experience. In fact, it suggests that reality has 10 or even 11 dimensions. Most of these dimensions are curled up so tightly we can never see them, like threads wrapped around the fabric of existence. These hidden dimensions are not empty. They shape the forces of nature themselves. Gravity, electromagnetism, the strong and weak nuclear forces, each emerges from the way these extra dimensions are twisted and folded. They are not theoretical decorations. They are the hidden engines of reality. But perhaps the most breathtaking implication of string theory is the idea of brains, short for membranes. In this framework, our entire universe may be a 3-dimensional brain floating within a higher dimensional space. Everything we know, stars, planets, galaxies, even light and time, exists only on this brain. Like a soap film suspended in invisible air, our universe may be just one sheet among many, drifting in a higher dimensional ocean. And if there are other brains, then the space between them, the bulk, could host physics utterly alien to our own. Now, imagine two such brains moving through this higher dimensional space. They drift for ages, silent and invisible to each other, until at last, they collide. The energy released in that moment would be unimaginable. And from the perspective of someone living inside one of the brains, that collision would look exactly like a Big Bang. Time would begin, space would expand, matter and energy would surge into existence. In this model, the birth of our universe was not the creation of everything from nothing, but the fiery consequence of two immense brains crashing together in a cosmic dance. This theory, called the ekpyrotic model, offers solutions to puzzles that have challenged cosmologists for decades. It explains the large-scale smoothness of the universe without requiring a sudden inflationary phase. It gives context to the Big Bang by placing it within a grander, older space. A space where universes are not born from void, but from movement, from impact, from the rhythm of higher dimensional objects colliding and rebounding. In this view, the cosmos is not a one-time event, but part of a cycle that stretches far beyond what we can observe. And what of the other brains? If they exist, they might be unimaginably close, just millimeters away in dimensions we cannot access. They could host other universes, with different particles, different forces, even different versions of time. Some physicists speculate that gravity might leak between brains, and that we might someday detect the influence of other universes brushing against ours. In this picture, we are no longer the center of existence, not even the center of a universe, but residents on a single membrane, adrift in a vast, unseen multiverse of brains. And our origin, a single cosmic collision that echoed across eternity. What if the Big Bang was not the beginning? What if it was only a chapter, a single heartbeat in an eternal rhythm far older than our universe itself? Some physicists propose that the cosmos did not emerge once from nothing, but rises and falls in an endless cycle. In this vision, the universe expands, grows cold and diffuse, then contracts again under its own gravity, collapsing into a dense state, only to rebound in another Big Bang. This is the Cyclic Universe model, reality as a cosmic heartbeat, pulsing through epochs beyond imagination. In this view, time does not end at the final collapse. It flows through the bounce like water through a narrowing channel. The laws of physics may carry over from one cycle to the next, with slight variations that evolve with each rebirth. Galaxies form, stars burn, civilizations rise and fall, again and again. The Big Bang becomes not a moment of pure creation, but a point of transformation, a bridge between what came before and what comes after. A turning point in a universe that never truly began and may never truly end. Modern versions of the cyclic model incorporate dark energy, suggesting that cosmic expansion could slow and reverse if the nature of that mysterious force changes over vast timescales. Some cycles may last trillions of years, others much longer. Perhaps each bounce gives rise to more complexity, more consciousness, more ways for the universe to know itself. In this grand cosmic loop, we are not living at the start of time, but somewhere in the middle, part of a story that has played out countless times before and may echo again forever. At first glance, our universe appears solid, three-dimensional, and deeply real. We move through space, experience time, and build our lives on what feels like firm physical ground. But what if this experience is only a projection, a kind of illusion cast from a deeper, hidden reality? This is not fantasy. It is a serious idea in modern physics called the Holographic Principle, and it suggests that everything we see, touch, and experience might emerge from information encoded on a distant two-dimensional boundary. The story begins with black holes. In the 1970s, physicists discovered something deeply unsettling. When matter falls into a black hole, its information seems to vanish forever. But quantum mechanics insists that information cannot be destroyed. This led to a paradox that shook the foundations of physics. The solution? Information is not lost. It is stored on the event horizon, the two-dimensional surface of the black hole. The interior might vanish, but the surface remembers. From this insight, a bold question emerged. Could the entire universe work the same way? What if all the information in our three-dimensional reality is actually encoded on a cosmic horizon far beyond what we can see? Just like a hologram stores a complete three-dimensional image on a flat sheet of film, the universe we inhabit could be the projection of information that exists elsewhere, on a vast two-dimensional surface at the edge of the observable cosmos. We would not know it, because every moment of our lives would be part of the projection. Everything, from stars to memories to thought, might be rendered from patterns written on a surface we will never reach. This idea is not only philosophically strange, it is supported by serious mathematics. Theoretical physicists studying quantum gravity and string theory have found that many equations describing gravity in three dimensions have exact equivalents in lower dimensions. It is as if the laws of physics themselves are hinting at a hidden layer beneath reality, where fewer dimensions contain the full story. In this picture, space itself is not fundamental. It emerges from quantum information, entanglement patterns connecting distant points, giving rise to the illusion of volume and distance. The implications of the holographic universe are staggering. It means that what we call here and now might be the result of data processing. That space and time, as we know them, arise from relationships between bits of information on a cosmic screen. Some scientists even suggest that consciousness itself might be part of this projection, an emergent phenomenon from the interaction of deeper informational structures. If so, the boundary between mind and universe begins to dissolve. We would not just live inside the hologram, we would be part of the code. And yet, this picture also offers a strange comfort. It means that reality is not fragile. It is deeply encoded, preserved, and unified. If our universe is a hologram, then everything we do, every thought, every moment, is part of an intricate, cosmic computation running on the edge of existence. The more we understand the code, the closer we come to understanding not just the world around us, but the very logic from which it is built. And if this principle is true, then the surface is not a limit. It is the source. What we perceive as the vast three-dimensional universe may only be the shadow of something far deeper. We live our lives bound to time. It shapes every memory, every plan, every heartbeat. We believe in a past that has already happened, a present we are moving through, and a future waiting to unfold. But what if this experience is an illusion? What if time, as we know it, does not truly exist? This is not poetry, it is physics. Some of the most profound theories in science suggest that time is not a fundamental ingredient of the universe, but something that emerges from deeper, timeless processes. Einstein's theory of general relativity revealed that time is not a constant flow, but a flexible dimension. It bends with gravity, stretches with speed, and fuses inseparably with space. In this framework, past, present, and future all coexist as part of a four-dimensional structure known as the block universe. From this view, time does not pass. It simply is. Every moment, from the first flicker of the Big Bang to the final dying star, exists simultaneously, like frames on a reel of film. We do not move through time. We experience slices of it. Quantum mechanics deepens this mystery. At the subatomic level, particles do not evolve through time in a simple sequence. Instead, they exist in superpositions, states that include multiple outcomes at once. Events only become definite when they are observed. Some interpretations suggest that time itself emerges only when information is exchanged between quantum systems. In other words, time may not be a backdrop against which events occur. It may be a side effect of events happening at all. The arrow of time, which gives us the feeling of cause and effect, is closely tied to entropy, the tendency of systems to move from order to disorder. But entropy is not a fundamental law. It is a statistical trend. If the universe were viewed from outside time, the direction of entropy would be just one detail among many. There would be no reason to say time must move forward. From a cosmic perspective, time may have no direction at all. Only our perception gives it flow. If time is not fundamental, then questions like, what came before the Big Bang, may be meaningless. The Big Bang may not mark the beginning of time, but the point at which time became a meaningful concept. Before that, reality may have existed in a timeless state where all possibilities coexisted and nothing happened, because happening requires time. In that state, there was no before, no ticking clock, no waiting, only potential. The mystery of time is not just about physics. It is about perception, consciousness, and the boundary between what is real and what only feels real. What is the universe made of? For centuries, we believed the answer was matter, atoms, particles, things we could touch and measure. Later, we added forces, energy, fields. But now, a new idea is emerging from the heart of physics, one that goes deeper than particles or energy, one that suggests everything in the universe, every star, every cell, every thought, is built not from stuff, but from bits, from information. In this view, reality itself is made of knowledge, not knowledge in our minds, but raw mathematical information woven into the fabric of existence. Think of a single hydrogen atom. It seems simple, one proton, one electron. But even this tiny system holds precise information: the position of the electron, its energy level, its spin, its quantum phase. All of these characteristics can be described in terms of data. Now multiply that by every atom in every galaxy across the cosmos. The amount of information contained within our universe is staggering beyond comprehension. But here is the twist. Many physicists now believe that this information is not carried by matter. It is the matter. Particles are not things that contain information. They are what information looks like when it becomes real. Quantum mechanics reinforces this view. In the quantum world, the properties of a particle are defined not by fixed values, but by probabilities. And what determines those probabilities? Information. The more you know about one property, the less you can know about another. This is not a limit of measurement. It is a feature of reality. Information defines the particle. Until it is measured, it exists as a cloud of potential outcomes. Only when a measurement extracts information does one possibility become actual. In this sense, reality emerges from questions asked and answered. Even space and time may be encoded with information. In black hole physics, we discovered that the surface area of a black hole, the event horizon, stores all the information about what has fallen into it. Not the volume, but the boundary. This led to the holographic principle, the idea that all the information in a region of space can be stored on a two-dimensional surface. Space itself may be emergent, rising from networks of entangled information, much like pixels on a screen. If this is true, then the universe is not a thing expanding in space. It is information unfolding in logic. This leads to a strange but powerful possibility. Information may be the only truly conserved quantity in the cosmos. Matter can be transformed, energy can be lost, but information remains. Even when stars die, when black holes evaporate, the information they carried is never erased. It may be scrambled, hidden, or encoded in radiation, but it is still there. In this view, reality is not a process of creation and destruction, but of transformation and rearrangement. The entire universe may be a computation, a vast, evolving system of logic processing itself. And where does consciousness fit in? If information is the foundation of everything, then minds, our thoughts, memories, choices, are patterns of information processing. The brain is not just a biological machine. It is a living structure that organizes and manipulates information. Perhaps consciousness itself is what it feels like when information becomes aware of itself. In that sense, the universe is not only made of information, it is learning, evolving, and observing. And we, as conscious beings, are its latest expression. Information experiencing information from the inside. In our everyday lives, it feels natural to assume that the world exists independently of us. Trees sway, stars shine, particles collide, whether we look at them or not. But the closer we examine the foundations of physics, the more that assumption begins to crack. At the heart of quantum mechanics lies a mystery. Reality does not fully take shape until it is observed. Particles remain in multiple states, existing in clouds of possibility, until someone, measures them. The act of observation seems to collapse the indefinite into the definite. It is as if the universe waits for a witness. The famous double-slit experiment captures this paradox with eerie simplicity. Fire single electrons through two narrow slits, and they form an interference pattern, as if each electron passes through both slits at once. But the moment we try to observe which slit it goes through, the pattern vanishes. The electron chooses one path. Reality shifts. It is not merely the measuring device that causes this collapse. It is the presence of information, and perhaps the conscious mind that interprets it. The observer does not disturb the system, it defines it. This strange link between observation and reality has led some physicists to propose a radical idea: that consciousness is not a byproduct of matter, but a fundamental feature of the universe. That reality itself may not exist in any definite form without the presence of a conscious observer. In this view, consciousness is not just watching the play, it is part of the script, helping to write the unfolding story of the cosmos. Each act of awareness, each moment of focused attention, participates in sculpting the world we experience. If this is true, then consciousness is not a passive witness to the universe. It is a co-creator. Every time we observe, we are not only learning about reality, we are helping it take form. This idea blurs the boundary between physics and philosophy, between science and self. It suggests that the deepest structure of the universe might not be atoms or strings, but experience, moments of knowing, woven together across space and time. In such a cosmos, meaning is not a human invention. It is built into the very nature of reality itself. We may never fully understand how consciousness interacts with the quantum world, but the evidence points to something extraordinary: that we are not isolated minds adrift in a mechanical universe, but living participants in a grand and mysterious process. The universe does not simply exist. It becomes through the lens of conscious observation. And in every choice, every question, every act of attention, we help bring reality into focus, not as spectators, but as creators. We are taught that cause comes before effect. First, the match is struck, then the fire appears. This idea is so deeply embedded in our thinking that we rarely question it. Time, we believe, flows in one direction, from past to future, never the other way around. But quantum physics suggests something stranger. In certain experiments, choices made in the present seem to influence outcomes that, by all logic, should have already been determined. The effect appears to reach backward in time. This phenomenon is known as retrocausality. One example arises in the delayed choice quantum eraser experiment. A particle passes through a double-slit setup, and a decision is made after it has already passed, whether or not to preserve which path information. Astonishingly, this future decision seems to influence the earlier behavior of the particle. The interference pattern appears or disappears depending on what is done later. It is as if the particle waits to know how it should have behaved. Reality, at the quantum level, does not lock itself in until the very last moment, even if that moment occurs after the event. Some physicists suggest this is simply a trick of interpretation, that no information actually travels backward in time, but others entertain the possibility that retrocausality may be real, that the future and the past are more entangled than we imagine. If time is not fundamental, as some theories suggest, then what we call past and future may be two faces of the same underlying structure. In this view, causes and effects are not lined up in a strict sequence. They are woven together in a web where information can flow in unexpected ways. This becomes even more provocative when we bring consciousness into the picture. If observation collapses quantum possibilities into definite realities, then the moment of observation carries weight, not just for the present, but potentially for the past as well. It raises the question, could a conscious act of observation reach back and determine how history unfolded? Not in a mystical sense, but as a feature of how quantum information behaves. If true, this would mean that consciousness does not merely witness the world. It participates in choosing which version of the past becomes real. Retrocausality challenges our most basic intuitions. It bends the arrow of time and blurs the line between memory and choice. It suggests that we may live in a universe where the future is not just shaped by the past, but where the past might be shaped by what is yet to come. And if consciousness plays a role in selecting realities, then the observer does not only look back through time, they might also reach into it, rewriting the cosmic script, one observation at a time. Imagine absolute nothingness, not empty space, not darkness, not silence, but a complete absence of existence. No time, no space, no energy, no possibility. A state so blank that even the concept of nothing feels too much. It seems like the most stable condition imaginable. After all, with nothing in it, what could possibly change? But according to modern physics, that idea is wrong. True nothingness is not stable. In fact, it may be the most unstable condition of all. The laws of quantum mechanics suggest that nothingness cannot remain nothing, not even for a moment. The reason lies in the uncertainty principle. This fundamental law of nature says that certain properties, like energy and time, cannot both be known with absolute precision. If you try to pin energy to exactly zero, time becomes completely uncertain. And from this uncertainty, something emerges. Even in a perfect vacuum, virtual particles can appear, exist briefly, and vanish again. These are not science fiction. They are real, measurable effects. They suggest that even nothing is not empty. It seethes with potential. It is always on the verge of becoming something. Quantum field theory tells us that every point in space is filled with fields, even if those fields have no energy. These fields are never truly at rest. They ripple with spontaneous fluctuations. When two metal plates are placed extremely close together in a vacuum, they are pushed toward each other, not by any force we can see, but by the quantum vacuum itself. This is the Casimir effect, and it proves that so-called empty space is not truly empty. Now take away space. Take away the plates. Take away everything. The fluctuations remain. From this perspective, nothingness is not the ground state of reality. It is a temporary illusion, a delicate balance that cannot last. The deeper truth is that the universe does not need a cause to begin. If the quantum vacuum exists even in the absence of space and time, then fluctuations can spontaneously erupt into being. One of those fluctuations, for reasons still hidden to us, may have grown. Inflation stretched it, gravity shaped it, and the universe was born, not from something, not from a creator, but from the instability of nothing itself. This idea is not merely speculative. It emerges from the mathematics of quantum cosmology and inflation theory. If a quantum fluctuation becomes large enough, fast enough, it can outrun the requirement to cancel itself out. It becomes real. It separates from the background of nothingness and evolves into a universe. This may have happened once. It may be happening always. In this view, our cosmos is not a miracle of creation, but a natural consequence of nothing being unable to stay still. The universe is what happens when nothing breaks the rules. So, when we ask, why is there something rather than nothing? The answer may be simple. Because nothing is forbidden, not by a deity, not by chance, but by the laws of quantum mechanics. Nothingness is unstable. It cannot hold. It cannot last. It cracks. It flickers. It births. And in that flicker, existence begins. Not with a thunderous command, but with a quantum whisper, one that continues to echo across time, across galaxies, and perhaps across many universes we have yet to imagine. The universe feels stable. Stars shine, planets spin, atoms hold together. But beneath this apparent order may lie a terrifying possibility, one so silent, so sudden, that it could end everything without warning. It is called vacuum decay, and it begins with a simple question. Is our universe truly in its most stable state? Physicists now believe the answer may be no. Our cosmos might be living on borrowed time, perched in what is known as a false vacuum, a temporary state that only appears stable, but is destined to collapse. At the heart of this idea lies the Higgs field, the invisible energy field that gives particles their mass. Current measurements suggest the Higgs sits at a peculiar value, one that implies our universe is not in the lowest possible energy state. If a deeper, more stable vacuum exists, then sooner or later, quantum tunneling could trigger a transition. In an instant, a bubble of true vacuum would form. It would expand at the speed of light, rewriting the laws of physics inside it and obliterating everything in its path, without warning, without pain, and without escape. We would not see it coming. Because the bubble travels at light speed, it outruns any signal. The moment it arrives, it is already too late. Inside the bubble, particles may not exist as we know them. Chemistry would fail. Atoms would dissolve. Space and time themselves could unravel. This is not science fiction. It is a serious consequence of the mathematics of quantum fields. The stability of the vacuum determines the stability of reality. And if the vacuum is unstable, then so is everything built upon it. Some theorists believe that vacuum decay could have already begun in a distant corner of the universe, expanding toward us even now. Others argue that high-energy events, like those near black holes or inside particle accelerators, could push the Higgs field over the edge. Fortunately, cosmic rays bombard Earth with energies far beyond anything we can create, and the universe has survived. For now. But the mere fact that vacuum decay is possible changes our understanding of cosmic permanence. What seems eternal may, in truth, be fragile. In the grand story of the universe, vacuum decay is the final twist. The idea that destruction is not something that comes from outside, but from the very fabric of space itself. The vacuum, once thought to be empty and harmless, may be a ticking time bomb written into the code of existence. The same quantum rules that once gave rise to the universe might one day erase it. Not with fire, not with collapse, but with silence and with absolute transformation. The deeper we explore the laws of nature, the more an unsettling pattern emerges. The universe appears to be astonishingly fine-tuned for the existence of life. Change any one of its fundamental constants by the smallest margin, and the cosmos as we know it collapses. Stars would not form. Atoms would not bind. Chemistry would be impossible. Conscious observers like us could never exist. It is as if the dials of the universe were set with extraordinary precision, too precise, perhaps, to be mere accident. Consider gravity. It is the weakest of the known forces, yet if it were even slightly stronger, stars would burn too hot and too quickly for complex life to evolve. Make it slightly weaker, and stars would never ignite at all. The electromagnetic force also dances on a knife's edge. A minor increase, and electrons would cling too tightly to nuclei. A minor decrease, and atoms would not hold together. The strong nuclear force is even more delicate. Tweak it, and you erase either carbon or oxygen, both essential for life as we know it. And then there is the cosmological constant, the mysterious pressure driving the expansion of space. Quantum theory predicts it should be unimaginably large, but in reality, it is tiny, just enough to allow galaxies to form. No more, no less. If this value were changed by even a fraction of a fraction, the universe would be a lifeless fog or a violent explosion. This is perhaps the most baffling fine-tuning of all, and no known physical law demands it. It simply is, balanced, improbably, as if by design. Faced with these facts, science offers two main responses. One is the multiverse, the idea that there are countless universes, each with different parameters. In most, life is impossible. But in a few, like ours, the numbers happen to align. We observe a fine-tuned universe, not because it is special, but because it is the only kind of universe that allows us to exist and ask the question. This logic is known as the Anthropic Principle. We should not be surprised to find ourselves in a universe that allows for consciousness, because we could not exist in any other kind. But the Anthropic Principle raises philosophical discomfort. Is it truly an explanation, or simply an observation? Does it answer the mystery, or accept it as a condition of awareness? Some physicists go further, proposing that consciousness might play an even deeper role. In quantum theory, observation collapses possibilities into reality. Could it be that conscious beings do not merely find themselves in compatible universes, but help shape them through acts of observation? If so, fine-tuning might not just permit observers, it might require them. Whatever the answer, the mystery remains. The universe is not random chaos. It is ordered, stable, and remarkably conducive to life. The odds against that happening by chance appear astronomically small. Whether by chance, necessity, or something else entirely, we live in a reality that seems custom-built for minds to wonder about it. And in that wondering, we become part of the story. The universe allows us to exist, and in turn, we ask why it exists in this way. Perhaps the question itself is the key to the answer. We often think of consciousness as an accident, a byproduct of evolution, arising late in the cosmic story. But what if that view is backwards? What if consciousness is not the end result of the universe, but its purpose, its origin? Some physicists suggest that consciousness might be the missing piece, the one ingredient capable of linking the birth of the cosmos with its eventual fate. In this view, the Big Bang is not just a physical event. It is the first moment of awareness observing itself, reaching across the void, awakening. Imagine a reality in which the universe begins not in silence, but in perception. Before particles, before time, before space, there is a kind of awareness, not human, not biological, but fundamental. A field of pure potential, capable of collapsing infinite possibilities into a single experienced reality. Consciousness, in this sense, is not something that emerges from the universe. It is something the universe needs in order to exist. Observation is not passive. It is the act of creation itself. As we move forward in time, toward the cold future of stars burning out and galaxies drifting apart, the question returns. What happens to consciousness? Will it vanish into entropy or evolve into something new? Some theories suggest that advanced intelligence could survive the death of the universe, storing itself in quantum fields, shaping future realities. If consciousness endures, it may eventually reach back, not just through space, but through time, completing a circle, becoming the observer that sets the entire story in motion. In the beginning, there was nothing, but nothing could not hold. From its instability came fluctuation. From fluctuation came structure. From structure came life. And from life, awareness. Then the awareness asked, "Where did I come from?" and began a journey backward, through stars, atoms, time and space, searching for the first moment. What it found was not a beginning, but a mirror, a reflection of itself at the edge of time. The universe, it realized, was not a straight line. It was a loop, a question folded into an answer. Every law of physics, every constant, every galaxy seems tuned for this, for the emergence of minds that ask, wonder, and observe. Perhaps this is the great secret hiding beneath all complexity. That reality does not simply exist. It participates, it listens, and it responds. The act of asking may be the act of shaping. The observer and the observed, the subject and the cosmos. They are not separate things. They are entangled. They define one another eternally. So when we ask, what came before the Big Bang, we are not only asking about physics, we are asking about ourselves, about the nature of awareness, about the role of consciousness in the unfolding of everything. The question has no simple answer, because the question is the answer. We are not separate from the mystery. We are the mystery, awakening to itself. And in that awakening, the loop closes. From nothing to something. From silence to thought. From the unobserved to the observed. And back again. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.